In Module 3, we will discuss equations, inequalities, and problem solving. In the first section, we will mainly focus on the addition property of equality. Before we solve equations, let's define what an equation is. An equation is of the form expression equals expression. An equation contains an equal sign, and an expression does not. So on the left side of the page, you can see we have a few examples of equations, and in each of those statements, we have an equal sign. On the right, we have a few examples of expressions. We have terms, just like you would see on the left side, but we do not have an equal sign. And that is the one difference between equations and expressions. In Module 3, we will focus on one type of equation, and that is a linear equation in one variable. A linear equation in one variable can be written in the form ax plus b equals c, where a, b, and c just represent real numbers, where a cannot equal 0. If a were to equal 0, the variable would disappear, and we would only have a mathematical statement. The property that we will use to solve equations in this section is the addition property of equality. Essentially, this property tells us we can add or subtract the same number from both sides of the equation to create equivalent equations. For example, if we had the statement 5 equals 5, we could add 2 to each side of the equation, each side of the equal sign, and that would give us 7 equals 7. 7 equals 7 would be an equivalent equation to 5 equals 5. Using the addition property of equality, let's solve x minus 4 equals 7 for x. So when we say we want to solve for x, the answer will look like this. X equals something, and it should be a number. X should equal a number. And the way we're going to do that is by adding or subtracting the same number to each side of the equation in order to isolate x on one side or the other. So when we look at the initial equation, I'm just going to draw a vertical line through the equal sign so we can get a better idea of what it means to have x isolated. On the left side of the equation, we want x to be by itself, isolated. Currently, x is not by itself. We are subtracting 4 from x. We need to do something with that 4. We need to perform some operation on both sides of the equal sign so that minus 4 will move. To do that, we're going to perform the opposite. We're going to add the opposite or subtract the opposite on each side of the equation in order to move that 4. Because we are subtracting 4, we have a minus 4. Let's add 4 to both sides of the equation. When we do so, negative 4 and positive 4 are opposites. And if you remember, one property of opposites is when they are added together, they equal 0. Negative 4 plus 4 equals 0. And for that reason, we can cross out those values. 0 represents nothing, and so we don't need to write 0 on the next line. So on the left side of the equation, we're left with x. On the right side of the equation, we have 7 plus 4, which is 11. And we now have our equation in the form that we expected. X is by itself on one side of the equation. All the numbers are on the other side of the equation. We have x equals 11. We could verify this rather quickly, put 11 in the place of x in the original equation, and see that 11 minus 4 is 7. This is a good solution to this equation. Let's try another example. Negative 5/16 equals x minus 7/8. Again, for the first few examples, I will draw this vertical bar through the equal sign so we can see the difference between the left-hand side and the right-hand side and what it means to have x isolated. Now, in the last example, we isolated x on the left-hand side of the equation, and it worked out well. In this example, I'm going to isolate x on the right-hand side of the equation, simply because it is already on the right-hand side. And so if we can avoid moving our variable, that's really the best thing for us. So in this particular example, the only value, the only term keeping x from being by itself is the minus 7/8. Just like in the last example, I'm going to add the opposite to both sides of the equation. So we add 7/8 because we have a negative 7/8 in the original. On the right-hand side, negative 7/8 plus 7/8, those are opposites, so they cancel. Their sum is 0. We're left with just x on the right-hand side. On the left side, we have negative 5/16 plus 7/8. And that would be perfectly fine if we had common denominators. So off to the side, this is just some scratch work that is necessary in order to find the solution to this equation. Remember, when we have two fractions that do not have a common denominator, we must find the common denominator, which is the least common multiple between those two denominators. So we would do some work that was introduced in Module 1 and find that the LCD is 16. So we don't need to change the first fraction at all. We have negative 5/16. The second fraction needs to be rewritten as an equivalent fraction with the denominator of 16. And we find that by multiplying both top and bottom of the original by 2. 8 times 2 is 16. 7 times 2 is 14. And now that we have a common denominator, we write that denominator one time, perform our operation across the top. Negative 5 plus 14 is positive 9. Now, it's always a good idea to look at our numerator and denominator and make sure they do not share any like terms. In this case, they do not. So the answer will be 9/16. Now, because the equal sign has a law of symmetry, or the property of symmetry, we could rewrite this. Instead of 9/16 equals x, we could say x equals 9/16. It's okay to think of that as a mirror image. As long as we aren't changing any signs, we can flip what's on the left side with what's on the right side. That's perfectly fine. Here we have another example, and in this example we have x on both sides of the equal sign and numbers on both sides of the equal sign. We have 2/3 x plus 6 equals negative 1/3 x minus 8. Just for learning's sake, I'm going to draw a vertical line through the equal sign so we can separate the left side from the right side. And now it's up to us. We need to move all of our variables to one side so that the variable can be isolated and all the numbers to the other side. We have the option to move our variables left or our variables to the right. In this particular example, I will move my variables to the left. More times than not, that's how I will solve the problem, although it will be perfectly fine to solve the problem with the variables on the right side, just like we saw on the last example. So I will start by moving any variables on the right side of the equal sign to the left by adding the opposite coefficient. So since we have a negative 1/3 x, I will add a positive 1/3 x to both sides of the equation. It's very important that you do it to both sides and not twice on the same side. So on the right side of the equation, negative 1/3 x plus positive 1/3 x, those cancel. Those are opposites. And we're left with a negative 8. On the left-hand side of the equation, 2/3 x plus 1/3 x equals 3/3 x, or 1x. We'll also have a plus 6. Now, to continue isolating x, remember, we want x by itself on one side of the equation. On this particular example, the left side. So we perform the opposite operation for the number. We have a plus 6. We're going to subtract 6 on both sides. Positive 6 minus 6, those cancel. On the left side, we're left with x. We have the equal sign. Negative 8 minus 6 is negative 14. Let's try another example. Here we have 6z plus 2 minus z equals 8 plus 4z plus 1. Now in this particular example, it looks like we can combine some like terms on the left side and maybe some like terms on the right side before we start moving numbers and variables in order to isolate our terms. So starting on the left-hand side of the equation, I have negative z, and I have a positive 6z. Combining those, I have 6 minus 1 gives me 5z plus 2 equals. On the right-hand side of the equation, we can combine 8 and 1. 8 and 1 gives us 9, so we have 9 plus 4z. Now we continue in the process to move all of our variables to one side, all of our numbers to the other. I will continue to move my variables to the left side and my numbers to the right side of the equation. So moving my variables to the left, I add the opposite. Or in this case, I subtract 4z. We had a positive 4. We need a negative 4 to cancel. On the right side, 4z minus 4z. Those are opposites, so they cancel. On the right side, 5z minus 4z is 1z, or just z. Everything else stays the same. Now z, all of the z's are combined on the left side of the equation. Let's isolate z by moving the 2. So we subtract 2 because minus 2 is the opposite of positive 2. On the left side, 2 minus 2 cancels. On the right side, 9 minus 2 is 7. So we're left with z equals 7. And that will be the solution. Our next example, 2/5 z plus 1/6 equals negative 3/5 z plus 1/3. Now for this example, we could go through the exact same steps that we had in the previous example, but I know many of you do not like working with fractions. So quickly, I'm going to show you one method for eliminating all of the fractions in your equation before you start working. To eliminate the fractions, we need to find the LCD of all denominators involved. In this example, we have 5, we have 6, and we have 3. So we would need to find the least common multiple of 5, 6, and 3. After you spend some time making your factor trees, multiplying your prime factors together, you would find that the least common denominator is 30. Now, once we find the least common denominator, we will multiply every term, whether it's a fraction or a whole number. We will multiply every term by that least common denominator. So 30 times 2/5 z plus 30 times 1/6 equals 30 times negative 3/5 z plus 30 times 1/3. Now remember, when we multiply a whole number times a fraction, it's easiest to turn the whole number into a fraction. So every time I wrote 30, I'm going to rewrite that as 30 over 1. And then we will multiply the numerators together, multiply the denominators together, and simplify. So we start with 30 times 2 is 60, over 1 times 5 is 5, z plus 30 over 6, again multiplying numerators and multiplying denominators, equals negative 90 over 5 z plus 30 over 3. Now the nice thing about multiplying every term by the LCD is once we simplify each fraction, we will have nothing but integers. 60 divided by 5 is 12, so this becomes 12z plus 30 divided by 6 is 5. So we have 12z plus 5. We go to the other side of the equation. Negative 90 divided by 5 is negative 18. We have z plus 10. At this point, we are adding our z's to one side. So we have z's on one side of the equation. We want numbers on the other side of the equation. So now, let's move the 18z from the right side to the left side. We'll do that by changing the sign. So we add 18z. 18z's cancel on the right side. On the left side, we now have 30z plus 5. That equals 10. Let's rewrite this equation to the right just so we have room to finish. 30z plus 5 equals 10. We can now subtract 5 from each side. The 5's cancel on the left. We have 30z equals 5. Now this is a situation we have not seen yet in this section. That will actually be introduced in the next section. Once we have z's on one side of the equation and numbers on the other, what we do when we have a coefficient of z that is not 1. But because we multiplied by an LCD, that was the result of this problem. So when we multiply z by a coefficient, the way we solve for z or isolate z so that it is completely by itself is to divide by the number that we were multiplying by. We do the opposite. We were multiplying by 30, now we divide both sides by 30. So on the left side, the 30's cancel, or they divide out to become 1, and we have z equals 5 over 30. Don't put this in your calculator and get a decimal. Leave it as a fraction, and then we will reduce that fraction. We write the prime factorizations, cancel the common factors, and multiply what's left. So in this case, z will equal 1/6. Let's try a few more examples. In this example, we see we have parentheses being multiplied by whole numbers or by integers. So we will need to use the distributive property multiple times on each side of the equation to simplify before we can solve. So starting with the 7, we multiply 7 into the parentheses. That will give us 7m minus 35. We're going to do the same thing with our 2. 2 times 8, 2 times negative 4m. So plus 16 minus 8m equals, on the other side of the equation, distribute the negative 2. Negative 2m, negative 2 times negative 2 is positive 4, and the 3 doesn't get multiplied, it just carries down. Now that we have distributed to remove all of the parentheses, let's combine like terms. Draw my vertical sign through my equals, my vertical line through my equal sign, so we don't confuse the left-hand side and the right-hand side. On the left side, we have 7m, and we have minus 8m. 7 minus 8 is negative 1, so negative 1m, or negative m, you can write it either way. We also have a negative 35 and a positive 16. We put those together to get negative 19. On the right side of the equation, we have a positive 4 and a positive 3. That will give us positive 7, so negative 2m plus 7. Now, again, I'm going to draw my vertical line through the equal sign. Let's move the m's to the left side, the numbers to the right side. So we do the opposite operation on m. We say plus 2m because 2m and negative 2m are opposites. So on the right side, the opposites cancel. On the left side, negative 1m plus 2m gives us a positive 1m, or just m. Everything else stays the same. So m minus 19 equals 7. To move the 19, we add 19 to both sides because 19 and negative 19 are opposites. So the 19 and negative 19 cancel on the left side. And we're left with m equals 7 plus 19, or 26. Let's try a few word problems. The Verrazano-Narrows Bridge in New York City is the longest suspension bridge in North America. The Golden Gate Bridge in San Francisco is 60 feet shorter than the Verrazano-Narrows Bridge. If the length of the Verrazano-Narrows Bridge is m feet, Express the length of the Golden Gate Bridge as an algebraic expression in M. Okay, let's start here. Algebraic expression. Remember, an expression does not have an equal sign. Now let's go back through the problem and let's find the important pieces of information. We are told that the Golden Gate Bridge is 60 feet shorter than the Verrazano Narrows Bridge. Now, if something is 60 feet shorter, we would subtract that from the other's length. It tells us that the bridge in New York City is M feet long. So if we start with the longer bridge, which is M, and we subtract 60, that will give us the length of the Golden Gate Bridge. And that is exactly what we're being asked to find. Express the length of the Golden Gate Bridge. So this algebraic expression in terms of M, which just means that M will be part of the expression, represents the length of the Golden Gate Bridge, and we are finished. Let's try another example. A 15-foot board is cut into 2 pieces. If one piece is x feet long, express the other length in terms of x. So looking at the picture, we can tell that the entire length of the board, 15, should equal the sum of both of the smaller pieces, the x and the question mark. That kind of makes sense. If we take the 2 shorter pieces and we add those together, it should add up to the length of the board, which in the problem we are told is 15. Now, in order to express the other length, and here the other length, that means the question mark. If we want to express the question mark in terms of x, really we're solving this equation for the question mark. So we need to move x in order to isolate the question mark. So we perform the opposite operation. We subtract x from each side because x and negative x cancel. So on the right-hand side, we're left with the question mark. On the left-hand side, we have 15 minus x, but those are not like terms, so we just have to write them beside one another. So the question mark, the other length, written in terms of x, is 15 minus x. We don't know the exact length of either piece of board, but now we know the length of the second piece in terms of the first piece, which was x. Let's try one more word problem. The area of a desert in Africa is 11 times the area of a desert in Asia. If the area of a desert in Asia is y square miles, express the area of a desert in Africa as an algebraic expression in y. So this kind of gives us direction on what our answer should look like. And what we're trying to find is the area of a desert in Africa. So let's go back through the problem and find the important pieces of information. We are told that the desert in Africa is 11 times the area of the desert in Asia, and that the area of a desert in Asia is y. So the area of a desert in Africa is 11 times y, or just 11y. Word problems intimidate many students, but as long as you take your time, read the problem, and will be patient while you sift through the information, some of it's nonsense, but sift through the information to find the valuable parts, it may not take you much time. Make sure to work hard, ask questions when you have them, and do the best that you can.